So in order to measure the hydraulic conductivity in the vadose zone, we need to take a look at basically what's controlling the flow in the vadose zone in the first place. So if we just take a step back, the flow in the vicinity of an instrument is going to depend on the head that we applied, the geometry of the instrument. It'll probably change with time, and it'll depend on the soil properties. So all four of these things. Okay, so with that in mind, what a permeameter will do is we'll set it up so it controls the geometry and the head. So we take these guys and we recognize those are important, and so we'll just set up a configuration so we control those. And then we'll measure the flow rate that's going in at this constant head, and we'll see how it changes with time. Okay, and then we're basically controlling for all of these things, and we then solve for what the soil properties are. Okay, so that's going to be the general properties or the general approach. And I guess one thing, let me just emphasize, we're going to control the geometry, and we fix the hydraulic head and measure the flow rate. Okay, that'll be how we do it in really both of the two instruments that we use. The Marriott bubbler will end up being an important device in these permeameters, and it's a very simple device, but it has some subtleties in how it works. So let me just describe it. If you have a tube here, and there's another tube that goes out the bottom, and a tube that enters the top here. And both of these tubes, both of the small tubes, are open. And so we can fill this thing up with water like I've shown here. And we might imagine that we've got our finger over the bottom tube. And so everything is stationary. So that would be step one. We fill it up with water like I've shown there. So what happens then when I take my finger off the tube at the bottom, what happens is the water level in this inner tube, it drops. So it drops down to here. And remember, this is attached, or this is connected to the atmosphere. So this is at atmospheric pressure, ATM. So at this snapshot in time, we've got atmospheric pressure right here at the bottom. What that means is that there's atmospheric pressure here inside of this tube, in the water. Okay, so if there's atmospheric pressure there, that must mean that there's less than atmospheric pressure there, and even less up here. And so what must be happening is that the pressure here in this headspace is suction, it's negative, and it equals that value, that much negative pressure head. Okay, so that's going to be the configuration at this instant in time. And we have a little bit of water flowing out here to allow that to occur. And basically, we've drained out this inner tube. Okay, so the Marriott bubbler is about set to start running, because in the next instant what happens is the air comes out of the bottom of this tube, and we start to create bubbles that rise up and go up into the headspace. So that's what I show here. Bubbles coming out of the central tube and rising up. And what happens then is, as this bubble rises up, the pressure right here at the bottom of the tube, it stays at atmospheric pressure. So the pressure in the water here is atmospheric pressure, and the pressure up here in the headspace, it's going to be in suction. It'll be a vacuum. It'll be less than atmospheric pressure, and the pressure head up in this chamber will be equal to that much, the negative pressure head, or the suction up there in the headspace. Okay, and so as long as this happens, as long as we have bubbles coming out, what it means is that the pressure at this point right at the bottom of the tube, the pressure is held at atmospheric pressure. Okay? Well, the hydraulic head is equal to the pressure plus the elevation head. And so what it means is that the head is maintained at a constant value in this chamber. It's maintained at that value right there. So all the while this Marriott bubbler is operating, while it's bubbling, the head is maintained at the bottom of the tube, so long as this is connected to the atmosphere. Okay, so one of the things that we could do is just have the water flow out like I'm showing here. If the head here is fixed, the head at this tube is fixed, so there would be a head difference between this point right here and the end. That head difference stays fixed, and so what that means is that the flow coming out of this tube will stay constant. So this is a way of making a device, a very simple device, that will maintain a constant flow rate. Okay, so that's one possibility. Another possibility, though, is to place this whole device here in a borehole. And if we do that and let the water flow out, and if we do that, the water will fill up in the borehole and the water level will rise. And it rises until the water level in the borehole reaches the same level as the bottom of this inner tube. In which case, the head right here is equal to that, and the head on the inside is equal to this level. So the heads on the inside and outside are equal. And so there's no flow. But if this is a borehole, for example, and water will leak out of the borehole, then as the water leaks out, the water level will drop, and we'll have some water then flowing out of the Marriott bubbler to maintain the head constant. Okay, so we then look at the water level up here and watch it drop, and the rate at which it drops is the rate at which water is flowing out of the borehole. Okay, so this little simple configuration called a Marriott bubbler will allow us to hold the head constant in a borehole and measure the flow rate that it takes to do that. And that'll allow us to create a permeameter. So here's the Guelph permeameter. This is the Guelph permeameter. It's used to measure the saturated hydraulic conductivity at the bottom of a hole in the unsaturated zone. So we start off with a borehole, and then we put this device down to the bottom of it. You can see it's quite a long device, and right there, that's the bottom. It goes down to the bottom of the borehole, and this stuff is above ground, this wide body here. That stores water, and that's where we make the readings. And so here's a sketch of it, kind of a schematic. You can see it's in the borehole, and it's going to all the way to the bottom. It's resting on the bottom, and it consists basically of this outer tube. It's kind of wide up here, and it gets narrower down here where it goes down in the hole. It's a bit narrower, and then there's this inner tube right there. That inner tube goes through a seal, and you can pull that inner tube up. So you can grab a hold of it up here and lift it up. And the inner tube is open, and it goes all the way to the bottom, and that's the bubbler tube for the Marriott bubbler. So this whole thing, this whole contraption is a big Marriott bubbler. And so what happens is you put it in the hole, and you put it in the borehole, lower it to the bottom, and then you raise this inner tube. That's your bubbler tube, and the water level in the borehole rises to right here, to right at this point. And you can see that's the same level as the bottom of the tube. So you fill the borehole up to that level, and the water starts flowing out of the hole and into the soil. And so it goes out like this, and so on. And as it flows out, the water in the bubbler, as you can see up here, that's the chamber. It's filled with water, and that's dropping. So as the water is flowing into the soil, this level here is dropping. And it's graduated. You can see the graduations there. Right. See right there. And so you can read the water level, and you read it as a function of time, and that'll tell you how fast the water level is dropping, and that tells you how fast it's flowing into the soil. And so you watch this for a while and let it run and make the measurements, and you establish an equilibrium flow rate. So you determine what that equilibrium flow rate is, and then if you know what the hydraulic head is, and you know what the flow rate is, and you know what the geometry is, then you can analyze all of that and determine the hydraulic conductivity. And you can also estimate alpha, the decay in the relative permeability curve in some cases. So here's a little more detail. This is the data sheet, and let me erase this. So this is the data sheet that you use to write down the data in the field. And start off by filling out this header, and it's got stuff like the investigator and the date that are fairly obvious. You want to write down the depth of the hole, the radius, and the device has two reservoirs, so you want to say whether you're using both of them or the inner one only, and then there's a reservoir constant that you note there. So that's the header, and it's important to write down the depth of the hole because you can make a reading with the guelph permeameter when the borehole's at one depth, and then you can advance the hole down to a deeper depth and get the hydraulic conductivity at multiple depths. So when you're making a reading, you have the first setting of hydraulic head is here. That would be 5 centimeters. And so you set it up for 5 centimeters, and this is the time. You write that down, and this is the head. You write that down. The head is just the position on that graduated scale within the permeameter. And then this is a delta t, so that's the difference between two consecutive time readings. And this is delta h, the difference between two consecutive head readings, or it's actually the water level within the permeameter. It's not the not really a head. And so then you take the ratio of those two, and that gives you the velocity of drop. So you do that, and you look at at these numbers as you're doing this, and you wait for it to stabilize. And usually you want to have 3 consecutive readings when the rate of drop is within your level of uncertainty. So then you've got a stabilized reading, roughly a steady reading, and then you pull that inner tube up by 5 centimeters, and you have then a 10 centimeter setting. You repeat it, and this table here is the same as the one on the left side. And so your stabilized reading, then you write there, put it there. So that's the field data, and then to do the analysis, we've got a worksheet here that'll take you through the calculations. And if we look at the header up here, we've got some stuff to fill out. The reservoir constant, that's from the previous page. And we get the steady state flow rate, which is multiplying the reservoir constant times that rate of drop divided by 60. And so fill in those values. And then there are a couple of different ways to do this calculation. The best one is shown here. It's method 1. And what you need is to substitute in A here. This is R1 and R2 from the previous page. And then you go through and do the calculation. This is the formula. And this formula comes from the theoretical analysis of flow of water out of a borehole in the vadose zone. That analysis has all been done and distilled down to this simple equation. So you go through, plug it in, do the calculation, and put the value there. So this is the saturated hydraulic conductivity. And you can also calculate the matrix flux potential. And that's done with this calculation. And again, it's pretty straightforward substitution. So go through and try calculating that. And then alpha This is the exponent in the Gardner relative permeability formula, and you've just calculated the saturated conductivity and the matrix flux potential there. So you can substitute them in and calculate that alpha term. And you might also try calculating these other guys, but these will be the main ones that you want to do. Okay, so I would try that first. If you can get that to work, then that's going to be your best calculation. However, what happens is that in some cases, you see how you have this subtraction R2, 6.8 times R2 minus 9 times R1. Well, if R1 is larger than R2, R1 will be less than R2, but what can happen is this subtraction can create a negative number. Okay, and if that happens, then this calculation says that the hydraulic conductivity is negative. Well, the explanation for that is that there's maybe a heterogeneity in the borehole or in the vicinity of the borehole that's causing some non-ideal conditions. But we know that the hydraulic conductivity can't be negative. So if you do the calculation and you get that result, then you can't use this formula. If that's the case, then you would use this second method, method number 2. It only uses, well, it can use both the 5 centimeter reading and the 10 centimeter reading, but it only uses them one at a time. And here's the way it works. You substitute in these values here, and A, we saw R is either R1 or R2. H is whatever head we're using. Little r there is the radius of the borehole. Alpha star is down here. For this one, we're not going to be able to determine alpha, so we can just estimate it. And it will estimate it depending upon what the structure of the soil is. So for a structured soil, clay through loam, it would be alpha would be 0.12 per centimeter. Okay, so we'll go ahead and use that value, substitute that in there, and then go through and do the calculation. The only thing that we don't know about is C, and C is a coefficient that you have to look up off of a table. So let me show you about that. Here's the table for C. So what you do is H is the head in the well, and R is the radius of the well, and then you have to decide what kind of soil that you're working on: structured clay, unstructured clay, structured loam, or sands. Probably most of the soils around here would be a structured loam, so we would use this middle curve, determine this, and then we would go and get the C value that way. Okay, so if we have C, then we should know all of the terms here, and that'll give us a hydraulic conductivity. And what we can do is then have two calculations, one for the 5 centimeter reading and one for the 10 centimeter reading, and we could take their average. So you would do that here's for R1, and here it is for the next head, the R2 head. Okay, you could also try this calculation, the matrix flux potential, but I would probably focus on trying to get these values. What we find in doing this kind of test around here is that this works sometimes, but getting this negative result is fairly common, and so we often will resort to doing this calculation. But you should try doing both. It's a fairly easy calculation. The advantage of this one, if this works, then you can have a way of calculating this alpha term, and that'll give you what the relative permeability curve is, and so that's quite helpful. Okay, so there's another sheet on the worksheet that gives you a more general case for whatever size borehole you want and whatever different heads you want. And it's fairly easy to figure out if you need to use it. It's here, but I would recommend using the ones on the previous page. Now, one thing that I'd like to point out too is that these calculations have been put into an Excel spreadsheet. So I would urge you to try the calculations on the worksheet. They're pretty straightforward to do. You just need to do some simple substitutions. But then you can use this Excel worksheet and check yourself. So here's one of those single head methods, the other single head method, and you need to provide the information here in the green boxes, and it's described. It's the same information that you have in on that worksheet that I just talked about. And so this is a helpful tool for doing the calculations, and so you should try using it. It's posted in the module on hydraulic conductivity. The disk infiltrometer is another way to measure the hydraulic conductivity in the vadose zone. This device is intended to measure the hydraulic conductivity of a flat surface, like the ground surface, or a flat surface that you've created in a soil pit. This is a mini disc, and so this is a little over a foot long, roughly. It's pretty mini. It consists of 2 Marriott bubblers. So here's one Marriott bubbler. There's the air entry tube, and there's the bottom. And this is another Marriott bubbler. So the lower Marriott bubbler holds water that flows out through the bottom of this device and goes into the soil. The upper Marriott bubbler here, what it does is set a suction head for the lower Marriott. So remember when I explained about how the Marriott bubbler worked, I was assuming that bubbler tube was at atmospheric pressure. Well, this mini disc infiltrometer, this is a pretty clever design because the upper Marriott bubbler is used to create a suction for the bubbler tube for the lower Marriott bubbler. So this chamber right here, the airspace in the headspace there, is pulled under suction by the upper Marriott, and that allows the lower Marriott to be operated at several different suction heads. Okay, so we saw that hydraulic conductivity in the vadose zone will vary with suction head, and so this is a simple and very elegant way to vary the suction head during the test, and you can then get hydraulic conductivity at several different suction heads. One reason for doing this, for example, is there are often macropores or large cracks or wormholes in the vadose zone, and they drain with just a small amount of suction. So you could do a test with the mini disc infiltrometer with a low amount of suction and get one reading, and then do it at a higher amount of suction, and that would be enough of a suction to drain out the macropores, and so you would get another hydraulic conductivity that was for the matrix and did not involve the macropores. So you can then essentially isolate the effects of the macropores on the flow in the vadose zone. And that's often a very important thing to be able to do because the macropores may be playing an important role. So the disk infiltrometer is made by a company called Decagon, and Decagon has a nice video that explains how to use it, so I would recommend that you take a look at that video to see the details about the operation of the disk infiltrometer. The video by Decagon will be part of the module for the course.